Alright, so let's take a look at this first part. So vectors and the geometry of space. So in this chapter, we introduce vectors and coordinate systems for three-dimensional space. This will be the setting for our study of the calculus of functions of two variables in future videos. We'll go over that in a later series, because the graph of such a function is a surface in space. So in this chapter, we will see that vectors provide particularly simple descriptions of lines and planes in space. And examples of the surfaces and solids we study in this chapter are paraboloids used for satellite dishes. So here's a parabola, 3D parabola like this, and so on. So that's a 3D parabola. There, satellite dishes, and hyperboloids used for cooling towers of nuclear reactors. So notice this setup here is a hyperbola, and then you have it in 3D, and so on. And here's added a link to different shapes here. So here is a paraboloid, here's a sphere, and here's an ellipsoid. So here's in 2D, there's a parabola, there's a circle, there's an ellipse, and there's a hyperbola. Then here's in 3D, you could have this in separate parts like that. Yeah, this one, if you look at it this way, if you look at it from that way, you'll have two parts like that. Or you can have a hyperboloid like this. And there's the equations for them. There's a sphere, there's a paraboloid, and so anyways, continue further. So three-dimensional coordinate systems. So to locate a point in a plane, or just a flat sheet, so there's a plane like that. To locate a point, like that. What you'll need as well, two numbers are necessary. We know that any point in the plane can be represented as an ordered pair, for example, A, B, of real numbers, where A is the x-coordinate and B is the y-coordinate. For this reason, a plane is called two-dimensional. To locate a point in space, so in three-dimensional space, three numbers are required. And we represent any point in space by an ordered triplet, or an ordered triple, A, B, and C of real numbers. In order to represent points in space, we first choose a fixed point, call this O, the origin, and three directed lines through O that are perpendicular to each other, called the coordinate axis, and labeled the x-axis, y-axis, and z-axis. Usually we think of the x and y-axis as being horizontal, and the z-axis as being vertical. And we draw the orientation, not origination. So we draw the orientation of the axis as in the figure. So here's how it typically is shown. So there's the origin at the center there, and there's the y and x as the flat plane over there, and there's the z is the vertical over there. So these are the coordinate axes. And the direction of the z-axis is determined by the right-hand rule, and as illustrated below. So there's your right hand here. Notice the thumb sticks out, and typically you could also have the index finger stick out for the x-axis. Notice it curls around here from the x to the y, and there's the vertical is your thumb. So if you curl the fingers of your right hand around the z-axis in the direction of a 90 degree counterclockwise rotation from the positive x-axis, so from here to here is going to be at 90 degrees like that. So, or you could do it's 90 degrees like that. Just write this better. So this is a right angle, and this is, in other words, 90 degrees. Like that. To the positive y-axis, then your thumb points in the positive direction of the z-axis. So these are all the positive axes, like that. The three coordinate axis, the three coordinate axes or axis determine the three coordinate planes illustrated in the figure A below. So here's the coordinate planes. So this xy, we'll call this the xy plane over here, and there's the yz plane is vertical over there, and on this side you'll have the xz plane on this side here. So those are the planes there. And here's added more text. This is also from my calculus book. I just forgot to add it, but anyways here. So the xy plane, so this is the xy right here, is the plane that contains the x and y axis. So there's the x and y axes. And the yz plane contains the y and z axis. So there's the z and there's the y. And the xy plane, not the xy, the xz plane. XZ plane contains the X and Z axes. And these three coordinate planes divide space into 8 parts. So you have one here, then you have another one in the back, and here, 3, 4, and then you also have on the negative sides. So you're going to have another 5, 6, 7, and then behind that's going to be 8. So you're going to have 8 parts total, and those are called octants. And the first octant in the foreground, that's this right here, this is determined from the positive axis. So those are positive ones over there. And note here, so here we have a room there, so left wall, right wall, and there's a floor, and that's because, well, many people have some difficulty visualizing the diagrams of three-dimensional figures, so you may find it helpful to do the following, and you can see this figure B above. So look at the bottom corner of a room, so let's say here, call that, and call the corner the origin. And then the wall on your left is in the XZ plane, so there's the wall there, there's left wall. And the wall on your right is the YZ plane, so there's the right wall, and the floor is the XY plane. Yeah, and the x-axis runs along the intersection of the floor and the left wall. So there's the x-axis, and then the y is on the right wall there in the floor. And the y-axis runs up from the floor toward the ceiling. Yeah, this is the... Oops, actually no, that's the z-axis. It runs up from the floor toward the ceiling along the intersection of the two walls. The y-axis runs along the intersection of the floor and the right wall. So there's the y-axis, floor and right wall. The z is in between these left and right wall and goes up that, like that. Yeah, along the intersection of the two walls. And you are situated in the first octant. So you're inside this room right here, the first one. And you'll know that there's going to be, well, 8 rooms total. And you can now imagine 7 other rooms situated in the other 7 octants, 3 on the same floor and 4 on the floor below, all connected by the common corner point here. So if you're in this room, there's going to be another one here, and then 3, and then over here, and then at the bottom, you'll have 4 more underneath you. All right. All right, so now if P, capital P, is any point in space, let A be the directed distance from the YZ plane, and from the YZ plane to P, and let B be the distance from the XZ plane to P. And this word directed, I think the calculus just means perpendicular to it, or the shortest distance from that plane. And let C be the distance from the XY plane to P. And we'll illustrate this all soon. And then, we present the point P by the order triplet A, B, C of real numbers, and we call A, B, and C the coordinates of P. And A is the X coordinate, B is the Y coordinate, and C is the Z coordinate. Thus, to locate the point A, B, C, we can start at the origin O and move A units along the X axis, then B units parallel to the Y axis, and then C units parallel to the Z axis as in the figure below. So we'll put all these words into a drawing to make sense of it. So you'll have this Z axis like that, the vertical one. Now you're going to have our y-axis, the positive one here, and this is the origin 0, and there is our, this is going to be perpendicular to it. This is our x-axis like that. And let's say we have a point P in space here. So it's in 3D. We'll call this point P, A, B, C. All right, so let's go make a sense of what this says. So A is directed distance from the YZ plane. So if this is the YZ plane, is this set up across on this wall? So it's a distance from that, and that's again, that's just our X coordinate. In other words, that distance is going to be up to here somewhere, or so it's going to be up to here. But before that, so let's say we have this. I'm going to draw this all the way down here, all the way to the bottom, and then so let's say it hits the bottom here, and then draw this perpendicular. It's going to go all the way across here like that. Oops. Yeah, and this is parallel to this one right here. So this is parallel to this wall, and this one here is parallel to this, like that. Yeah, so then this distance from the ZY plane is the X coordinate, and in other words, we can start from the origin 0 and move A units along the X axis. So there's the A units, and then B units parallel to the Y axis, that's B. like that, and then C units parallel to the z-axis, like this. So B is going to be, this distance B is the distance from the zx plane, or the xz plane. Xz plane is B. And then C is the distance from the xy plane to P. So this is the xy plane, and there's a z. This is C, not z. Like that. And then C distance all the way up to there. Alright, so going further, so the point ABC determines a rectangular box, as in the figure below. So we have this right here. Let's draw this again, but now you can see that this can form a rectangular, a rectangular box. So we'll do that again. So we have the Z, like that, and then we're going to have our Y. I'm just going to make this, just a bit shorter. So this is our Y, and then this is going to be our X, like this. Whoops, this is going to be our X, like that. And let's say we have our point P across here. So this is our point P, and we're going to have a box. So let's draw this all in 3D. This goes down here. This goes, draw this a bit neater. So this is, let's say it goes here, and there is the line across, there's the line across, and then draw this all in 3D, like that. And then this goes across like that. This goes like that. There is our 3D box. All right, so there's our box, and this one we're going to call this P, A, B, C. All right, continuing further. So if we drop the vertical perpendicular line from P to the XY plane, so if we drop this line, just remove that. In other words, our vertical distance C becomes 0. We get a point Q with coordinates A, B, and 0 called the projection of P onto the XY plane. So that's this point right here. This is our point Q, like that. And we'll call this A, B, and then the vertical distance is 0, like that. And similarly, R, 0, B, C, and R, the points are A0, A0, C are the projections of P onto the YZ plane and XZ plane, respectively. So in other words, this one we're going to remove the this A value. That's this horizontal X coordinate from here to here. So in other words, we're going to get this point here. So actually, no, this one here. We're removing it, so we get this point here. This one's going to be our R, and then the X coordinate is 0. Everything else is the same, B and C, like that. And that's a projection onto the Z, onto the YZ plane. And that's right here, YZ plane. And then the next one is our S. We're going to drop this down. Yeah, we're going to drop the Y coordinate. So we're going to project it all the way onto this XZ plane, so the XZ plane. So we're going to drop this line, and we're going to go all the way up to here. So this is P, Q, R, and this one is S, like that. Now let's put this like this. This is going to be our S. This is going to be our A. 0 is the Y coordinate, and then this is going to be C, like that. All right, continuing further, so as numerical illustrations, the points right here, -4, 3, -5, and 3, -2, -6 are plotted in the figures below. So let's graph this one, or let's plot that point out first. So this one is, notice it's going to go -4, so we're going to go the negative x-axis, then it's going to be +3, and then this is negative. So in other words, it's going to be on the below these axes. This is the Z, it's going to be a -1. So let's say we have our Y like this, and we're going to have to extend this all the way down because it's going to be -Z. Just extend this down further. And we're also going negative X, so that's going to go backwards. So we're going to have to go from here. This is our X. But then we're going to have to go to the backwards side of it. So we're going to go -4. So let's put it all the way here. So we're going to go -4. And let's put that line here. And then we're going to go, so let's say all the way up to here. And then we're going to go +3 to the Y. Make it a bit shorter than that. So let's make it here. Let's go. Okay, this should be good. All right, so this is good enough. So there's 3 right there, and then we're gonna go all the way down. We're gonna go all the way down to -5. So let's say the point is all the way across here. We're going to be drawing in 3D. This goes, it's going to go behind it. So I'm going to break that apart. And yeah, here. So this is going to be -5 all the way down. And there's our point. -4, 3, and -5. And now let's draw this in 3D. Yeah, so to do that, let's draw our top part here and draw a parallel line like that. And this is going to go all the way down. And let's do this more down like that until this is parallel like that. And then we're going to have this line across here, parallel to that, a y-axis. And then behind it, we can have dashed lines, dash, 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 dash. And then this is going to be another dashed line like that. And then dashed line like that. All right, here. So I fixed that up and made it smaller just so we can fit this inside. It will fit the other one inside. So this one is going to be 3, -2, and -6. So it's also going to be below this. It's going to be below this floor because it's negative vertical. It's going to be it's going to be -6 there. But now it's going to be in the front, and then we're going to go backwards there. So let's draw this out. So we're going to do again the z-axis. But it's going to be on the negative y, so we could have a short z, we could have a short y, like that. And then it's going to be on the positive x, so we can make this super long. There's the x, like that, but it's going to be on the negative y. So make it like that, so negative y. So we're going to go to 3 here, let's say all the way to 3 here. And then we're going to go -2, we're going to go all the way across here, -2, and then we're going to go all the way back down, all the way until -6. So we're going to go all the way down, and we're going to go like this, -6, like that. And then draw this in 3D, and well, this is the point right there, and this is going to be our 3, -2, -6, like that. And then we're going to draw this all in. Let's make this bigger. And now we're going to draw it in 3D, so it's going to go like that. So it's going to go all the way down until it's parallel. Well, this one here as well. Until it's parallel. So all the way down like that. And yeah, this one across like that. So make this all the way down like that. Yeah, so it looks something like that. Now we draw this in 3D behind it. So this is going to be all the way down. Dot, 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 dot. Maybe all the way down like that somewhere. And this is going to be dot, 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 dot. And then dot, 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 dot. And yeah, here I just fixed it up, made it a bit smaller to match this. And yeah, so it looks like that in our rectangular box there. Well, anyways, let's continue further. So the following Cartesian product is the set of all ordered triples of real numbers and is denoted by this r to the power of 3. And this is the Latin capital R, usually written like that, which I sometimes just use r cubed there. And this Cartesian product, this is just written as r. Let's write this in the Latin form. R x r times r, and this equals to the set. We'll write it like this of all these points x, y, z, where x, y, and z are elements of real numbers. In other words, these are all just real numbers like that. So this is written like that. So this is the set where x, y, z, these are all just real numbers. Or it's a collection of all the points. And just for completeness, so this r times r times r, this is just indicating this is our r cubed equals all this. Alright, so now that we have this is just a set of all of these points, x, y, z, or of all these ordered triples, and we have given a 1-to-1 correspondence between points P in space and ordered triples A, B, C in R3, where these are just all real numbers inside here. So each point has a 1-to-1 correspondence with with these collection of triples right here, this x, y, z, and so on, for this A, B, C, and R cubed. So this is called a dimensional rectangular coordinate system. And notice that in terms of coordinates, the first octant can be described as the set of points whose coordinates are all positive. Remember, yeah, that's where all the positive axes are. In two-dimensional analytic geometry, the graph of an equation involving x and y is a curve in R squared. Yeah, curve, or just a line like that, just a curve. But in three-dimensional analytic geometry, an equation in x, y, and z represents a surface. So in 2D it looks like that. In 3D it's going to look like just an actual surface. So imagine this is in 3D. So a full surface.